Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element hafnium. I have a sample of hafnium right here in this vial. It's kind of shiny. I put it on my scanner so you could see it. Let's take a look at that. There it is. You can see it's a silvery metal. You may be able to see it a little bit better if I magnify it. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Hafnium is the 72nd element in the periodic table. Its atomic number is 72 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. These were the elements known to Mendeleev, the best-known creator of the periodic table. He predicted these 4 unknown elements would be found, and he predicted their qualities. He also suspected there may be an element similar to titanium and zirconium, but heavier. Turned out, he was right about all those. Edgar Smith, an American chemist, was most interested in the history of chemistry, but was also interested in the chemistry of rare earths, or lanthanides. From sand containing the mineral monazite, he extracted rare earths, and he set aside some of the leftovers. Monazite is a phosphate with lanthanum, cerium, praseodymium, and neodymium as major substituting elements, and most of the other rare earths as minor constituents. He knew there was zirconium in those leftovers, and he suspected another new element was in there too. He figured he would get to that element in his spare time. He never did. Henry Moseley was a brilliant English physicist, cut down in the prime of his life in World War I at the early age of 27. He examined elements using X-rays. He's responsible for changing the way the periodic table was arranged, from ordered by atomic weight to ordered by atomic number, the way we now use it. He was able to show gaps in the periodic table at elements 43, 61, 72, and 75. Those gaps led to a search for the missing elements. In 1921, Charles Bury said element 72 should resemble zirconium. In 1923, Niels Bohr agreed based on his theoretical model of the atom and with Moseley's X-ray spectroscopy data. Dirk Koster and George de Hevesy were motivated to search for the new element in zirconium ores. Hafnium was discovered by the two in 1923 in Copenhagen, Denmark, validating the original 1869 prediction of Mendeleev. It was ultimately found in the mineral zircon. Zircon is a zirconium silicate. Hafnium is a minor constituent of zircon and is very difficult to separate from the zirconium that makes up most of the mineral. Zirconium and hafnium have the same number of outer electrons, and their atoms are almost exactly the same size. This makes them both chemically and physically similar, so as I mentioned, they're very difficult to separate from each other. Jan Hendrik de Boer and Anton Edward van Arky first purified hafnium metal in 1924. They also perfected methods to produce very pure tungsten and titanium. The location where the discovery took place, the University of Copenhagen in Denmark, led to the element being named using the Latin word for Copenhagen, or hafnia, and hence hafnium. Copenhagen was the hometown of Niels Bohr, coincidentally. Hafnium is part of a large group in the middle of the periodic table called the transition metals. As I previously mentioned, the main commercial source of hafnium is from the mining of zircon for its zirconium content. Hafnium is really part of the leftovers from zirconium production. Oddly enough, both are used in the nuclear industry, which we'll discuss in a bit. In normal zircons, maybe 1% to 4% of the zirconium atoms are replaced with hafnium atoms. Another rare mineral, which looks almost identical to zircon, is hafnon. Remember that zircon is a zirconium silicate. In hafnon, the zirconium content is mostly replaced with hafnium. Again, exceedingly rare and not a commercial source, just a good example of how similar the two elements are. Hafnium is a shiny, silvery, ductile metal that's also corrosion resistant. The very pure piece on the left was remelted with an electron beam. The sample on the right has suffered some slight surface oxidizing, creating beautiful iridescent colors. Here are more slightly oxidized hafnium pellets. The thin oxide layer on the surface of these create color the same way bubbles create color, by interference of light. I couldn't resist including these, they're so beautiful. As with most elements, the price of hafnium varies widely with purity and the quantity you buy. 99% pure hafnium goes for between $2,000 and $4,900 per kilogram. Fairly expensive compared to many other elements. The element hafnium is fairly uncommon in the universe, coming in as the 67th most abundant element by mass at 7 parts per 10 billion. At 60th, hafnium is a bit more common in the Sun, but still only 1 part per billion. It's the 59th most abundant element in meteorites at 170 parts per billion. Surprisingly common compared to everywhere else, in the crust of the Earth, it's the 45th most common element at 3.3 parts per million, a little more common than tin at 2.2 parts per million. Hafnium is the 64th most abundant element in the oceans, virtually non-existent at 8 parts per trillion. And lastly, like most of the elements in the upper reaches of the periodic table, there's really no hafnium in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Hafnium is here. I understand this looks complicated, but let's look at just hafnium a little closer. The horizontal axis of this square represents time from the Big Bang to now. The vertical axis shows the proportion of hafnium created by various processes. About 3/5 of the hafnium present today is believed to be produced by dying low-mass stars, the magenta area, and about 2/5 is produced in supernovae, the yellow area. A very small portion, that green icing on the top, is produced in neutron star mergers. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same. 72 protons for hafnium. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 36 known isotopes of hafnium. Of these 36, there are 5 stable, non-radioactive isotopes. These 5 stable isotopes are found in different proportions in nature, from over 5% to over 35%. The observant among you will probably notice that these 5 isotopes do not add up to 100% of the hafnium in the universe, only 99.84%. Well, where's the missing 0.16% of naturally occurring hafnium? There's actually one very long-lived radioactive isotope that makes up the rest, hafnium-174. This isotope makes up the remaining 0.16%. More on this in the next slide. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of hafnium occupy the same place in the periodic table. Of the radioactive isotopes of hafnium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest hafnium half-life is hafnium-174, with a half-life of 70 quadrillion years. That's over 5 million times the age of the universe. With such a long half-life, you can see why hafnium-174 still occurs in nature. It hasn't had time to decay away yet. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we're going to be doing a lot of dividing by 2. If you waited one half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait one more half-life, half of that half decays, leaving you with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's 1 remaining atom after 10 half-lives? If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Hafnium has a fairly high density at 13.31 grams per cubic centimeter. As a reminder, water has a density of only 1 gram per cubic centimeter. I've put up more densities for you here. You can see that hafnium is denser than lead at 11.34 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself, but we'll have to wait to do this until we're back face to face. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, hafnium's density is 13.31 grams per cubic centimeter, the magenta circle between lead and tungsten. Unfortunately, I don't have a block of hafnium. Given its price, the block would cost over $2,200. Hafnium has a high melting point at 2,233 degrees Celsius, or 4,051 degrees Fahrenheit. It has the 10th highest melting point of the elements. It boils at a blistering 4,603 degrees Celsius, or 8,317 degrees Fahrenheit, making it the 8th highest boiling point of all the elements. That's a whopping 2,370 degrees Celsius above its melting point. Hafnium has the 13th largest liquid temperature range of all the elements. If we compare the size of the hafnium atom to that of hydrogen, we'd see something like this. The hafnium atom is about 4 times the size of hydrogen. By the way, a picometer is a trillionth of a meter. Atoms are exceedingly small. Here are atom sizes sorted from largest, cesium on the top left, to smallest, helium on the bottom right. Hafnium has the 18th largest size atom of the elements. Hafnium is a medium-hard element, coming in at 5.5 on Mohs scale of hardness, about the same as glass. Here's a chart of element hardness from the hardest, boron on the left, to the softest, cesium on the right. Obviously, I'm not including liquids or gases here. Hafnium is the 17th hardest element, between molybdenum and titanium. Hafnium has the seventh lowest rate of thermal expansion of all the elements, only about 6 parts per million per degree Celsius. This means that if you had a 1 meter long bar of hafnium and you heated it by 1 degree Celsius, it would get longer by only 6 millionths of a meter, or about 1/10 of a hair width. That's a pretty low expansion rate. Here's the periodic table of the spectra. Hafnium has a very complicated set of emission lines across the spectrum that can uniquely identify it to scientists. No other element gives off this set of colors. Let's take a look at a few applications of hafnium. Due to its price and chemical similarity to its sister element zirconium, there are only a few applications where actual hafnium is used rather than the less expensive relative. This application is a bit complicated to explain. As I said previously, both zirconium and hafnium are used in nuclear reactor cores, but for completely opposite purposes. While the two elements are physically and chemically very similar, they're very different atomically. Zirconium is almost completely transparent to neutrons, and hafnium absorbs neutrons extremely well. This graph shows how well neutrons are absorbed. You can ignore the neutron cross-section label here and just know that the elements near the top of the chart are good neutron absorbers and elements near the bottom are poor neutron absorbers. Hafnium is a good absorber and is used to control the reaction in the core of the reactor. Zirconium is a poor absorber. The silvery tubes you see here are zirconium, which contain the uranium fuel pellets. The tubes must allow through the neutrons from the fissioning uranium, so they must be made from hafnium-free zirconium. Control rods containing hafnium are interspersed among the fuel rods. These control rods, control how fast the fissioning reactions take place. Fission of the uranium atom happens when it's hit with a stray neutron. The extra neutron destabilizes the nucleus, which then splits into two smaller, lighter nuclei. The split, or fission, of the atom also releases several additional neutrons that are now free to cause more uranium atoms to fission. Since many neutrons are released by a single fissioning atom, and each neutron can cause a further uranium atom to fission, the reaction can grow exponentially, resulting in an uncontrolled release of energy. If you were developing a nuclear weapon, this is exactly what you want. In a nuclear reactor, it's the last thing you want. To control the fission reaction, you need to absorb a critical number of neutrons. Some elements, like hafnium, are very good neutron absorbers. In a nuclear reactor core, control rods of these absorbing elements, or their oxides, are interspersed among the uranium fuel rods. Pulling the control rods out of the core allows more neutron reactions to take place, heating up the core. Pushing the rods in slows the reaction, cooling the reactor. Most of the hafnium produced in the world goes into the manufacture of control rods for reactors. Hafnium is used in the core of plasma cutting electrodes because of its ability to shed electrons into the air, making a hot, low-resistance flow of electricity through the plasma. Not technically an application, pure zircons can be of gem quality. Depending on impurities, zircons can make beautiful gems of many different colors. Alloys using hafnium were used on the main engine liquid rocket nozzle of the Apollo lunar lander. This nozzle was made from 89% niobium, 10% hafnium, and 1% titanium, and could stand up to the wide temperature changes in a rocket nozzle. This is a CPU, or central processing unit, used in computers. It has layers of conducting or semiconducting material separated by insulating material. Hafnium oxide-based compounds can be used for the insulating portions of the very small components of today's processors. There was a big debate concerning hafnium that started in 1998. It was claimed that a certain radioactive isotope of excited hafnium could be stimulated to give up its stored energy by being hit with lower energy photons. Normally, there's not much you can do externally to stimulate a nucleus. In this case, it was claimed that by stimulating the nucleus this way, you could cause it to release high-energy gamma-ray photons, and the resulting gamma rays would be aligned like a laser. It was a big claim with lots of possibilities for both energy generation and weaponry. Unfortunately, no one was able to repeat the experiment, so, like cold fusion, it's still a bit of a controversy. And producing this isotope is very, very costly. You may have a tiny bit of hafnium inside you, possibly absorbed from the environment, but your body does not use hafnium, and it has no known biological functions. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about hafnium and the hafnium controversy. Yield the Holy Grail. Induced gamma emission. Let the price be low. In the next program in this series, I'll examine an important element of the electronics industry, tantalum. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element hafnium.